Okay, welcome back everyone. In this video, we're going to continue our discussion of universal gravity by discussing the motion of satellites. So we have a little picture here kind of showing us what's happening, and we'll be talking about this as we go. Okay, so how do we use Newton's laws of motion and gravity to analyze the motion of satellites, whether they are natural or artificial? And how do we use calculations of energy to determine the orbits that satellites follow? All right, so first of all, we can see here that a satellite will follow many different paths depending on its initial speed. Okay, so as v0 of the satellite increases, the trajectory changes from a parabola, and the parabola is going to be paths 1 and 2. Then it's going to turn into a circle at 3. Final, and whoops, 3 is also kind of an ellipse, but a circle is definitely a 4. Then we have an ellipse at 5, and then if we go fast enough, we get a hyperbola. Okay, now because of Newton's second law, we can calculate the speed required for a circular orbit. And the way that we do this is we say that the force of gravity is responsible for the centripetal motion. And so therefore g, mass of the Earth, mass of the satellite, over r squared is equal to m v squared over r. So we can cancel out an m and an r on each side and solve that for v. So g, mass of Earth, over r, square root, is our velocity for circular orbit. Okay, so this is very important. So this is v orbital for a circular orbit. Okay, so this r, again, is the center to center distance. And here's an app that kind of shows what's going on. Okay, and so what I can do is I can fire this object from with different velocities. Okay. Okay, so I'm not sure if this sound is coming through, but there's a sound when this is being launched. Let me check and enable that. Okay, so we don't really need to hear the sound for this, okay, but you can always search for Newtonian mountain, okay, and if I reset this and put a larger firing speed, whoops, I think that was a little bit too large. Let me reset that. We'll do a little bit slower, okay? This doesn't want to work right now. Okay, well, in any case, we can go back to this a little bit later, but we can see that as you increase the speed, we go from a parabola to a circle and then into an ellipse. So let's just go back to this and see if we can get it to work again. Okay, so let's do a little bit larger speed here. Not quite as much as before. Maybe we'll just do 6 kilometers per hour, 6 kilometers per second. And so we don't quite make it. Let's try about 8. Okay, and at 8, we have an ellipse. Okay, so then it's going to come back, and if you can hear the sound, they make a blood-curdling scream as it hits the guy in the back of the head. So I don't know if you heard that, but you can always go back and try that on your own. All right, so in any case, we can also determine escape velocity, which is the boundary between having an elliptical orbit and a hyperbolic orbit. So how fast does the object need to go to completely escape the gravitational pull of a planet or star? Well, if we escape completely, then at an infinite distance we have no potential energy, and at the same time we would be at the top of our path. It's like if you throw a ball into the air and it's slowing down and coming to a stop. So the velocity would be zero and the kinetic energy would also be zero. So the total energy of the object has to be zero. E equals U plus K, which equals zero. Now, using conservation of energy, we can figure out how much speed is required to escape. So if E initial is equal to E final, which is zero, then we can say that U initial, which will be negative GMM over R, plus K initial, which will be 1/2 times mv escape squared, is equal to 0, and that can get us our escape velocity of root 2gm over r. Okay, now let's compare this final result with orbital velocity, and notice that we're just off by a factor of 2. Okay, root 2, I should say. Now here's a summary of what orbital speeds give us which orbits. So first of all, if your speed is less than v orbital, which is this right here, you're going to get a parabola. If you're exactly equal to v orbital, you're going to get a circle. So these are all conic sections. If you're in between orbital and escape speed, remember that v escape is root 2 v orbital, which is root 2 gm over r. Okay, then you get an ellipse, and if you're greater, that should say greater than or equal to v escape, then you get a hyperbola. So the object will escape from its orbit. Okay, next, let's take a moment to look at the time and the energy in a circular orbit. So first of all, since the orbital speed v is 2 pi r over t, we can show that the period of an orbit is 2 pi r to the 3/2 over the square root of gm. Okay, so where does this come from? Well, remember in a previous slide we said that the force of gravity is equal to the centripetal force, and the centripetal force was mv squared over r. But since v is 2 pi r over t, we can just write that 2 pi r over t squared. And if you are able to hear sound on your computer, I just now heard a scream from like 5 minutes ago when the first ellipse that I sent, which had a very large orbit, finally came back and hit the guy in the back of the head. So I don't know if you're able to hear that. But anyways, this is going to be mv squared over r, and if we simplify this, then we're actually going to get an expression for t that looks like this. So t is proportional to r to the 3/2. Okay? Now, on the energy side of things, since total energy is kinetic plus potential, we can state that the total energy in an orbit is equal to gmem over 2r. Okay, so why is this energy negative? Well, let's think about this. Energy is equal to kinetic plus potential, so that's going to be 1/2 mv squared, and then potential is negative g mass of the earth, let's do capital E, m over r. But then we recognize that this v is actually orbital speed, okay, and remember v squared for orbital will turn into gm over r. So this is actually equal to 1/2 m times g mass of the earth over r minus g mass of the earth times m over r. And if you look at this, we really have 2r down here, so we put 2r here. Those two will combine to give us this. So that's how we get that. Okay, but now what's the meaning of this negative sign? Well, this negative sign means that we have a closed or a bound orbit. Okay, so if you happen to calculate that the total energy is equal to 0 or greater than 0, then you don't have a bound orbit, you have an open orbit, and that's when we have escape velocity occurring. Okay? And anytime you're between this value of E and 0, then you have an elliptical orbit. So it's kind of the same as the velocity. Okay, so let's look at one quick example. So we want to put a 1,000 kilogram satellite into a circular orbit 300 kilometers above the Earth's surface. So we want to know what speed, period, and radial acceleration will it have. Okay, so first of all, and I'm not going to plug in all the numbers, I'm just going to show you what we'll use. V orbital will be square root of g, mass of the Earth, over r. And that's going to be, so that's our 6.67 times 10 to the minus 11th. Okay, mass of the Earth is about 5.98 times 10 to the 24th kilograms. And that's a number that your book has, or you would just Google that. And then the r is 300 kilometers above the Earth's surface. So it's the radius of the Earth, so 6,380 kilometers, plus an additional 300. Okay, so those are all in meters if I add the 10 to the third. Okay, so that's something like 7,730 meters per second. Okay, if I want to get the time, well, that's just going to be 2 pi r over this v orbital, and you can plug that in. Just make sure that you use this value here for r. Okay, and then if we want the acceleration, that's just v squared over r. And again, you're using the same thing. This whole thing is going in for r. Okay, now in the second part, how much work must be done to put the satellite into orbit? Well, work is equal to the negative change in potential energy, which is going to be U initial minus U final. Now, U initial is going to be G, mass of the Earth, M, over, well, it's just going to be the radius of the Earth. But then we have to subtract from that G, mass of the Earth, mass of the satellite, over radius of the Earth plus the height. And in this case, the height is just 300 kilometers. So again, we won't plug in the numbers, but that's how you would set that up. Okay, so next time we're going to be talking about Kepler's laws of planetary motion.